The topic for today is Introduction to Vector Spaces. Now, a vector can be defined as a representation of a tuple in a dimensional space. Now, here we have dimension as n. So, in n dimension, that is Rn, we can define a vector as an ordered tuple of a sequence of n real numbers. Now, if we consider n is equal to 1, then it is a set of all real numbers. If we consider n is equal to 2, then it is set of all the ordered pairs of real numbers x1 comma x2. Now when considering n equal to 3, it will be a set of all the ordered triplets of real numbers like x1 comma x2 comma x3 and so on. Now in the representational space, we can represent a point x1 comma x2 with a vector as given in the figure. In 2D space and 3D space, we represent vectors in similar fashion as shown in these two figures. Now coming on to the properties of vectors. Vectors have certain properties like vector addition. Now considering two vectors w and v, w is having values w1 up till wn, and v is an ordered tuple of values v1 to vn. Now vector addition w plus v is equal to, then the answer will be w1 plus v1 comma w2 plus v2 up till wn plus vn. Now scalar multiplication. Now c is a constant, so when multiplying a constant with the vector v, we get the value as cv1 comma cv2 up till cvn. Equality. Two vectors w and v are equal if and only if w1 is equal to v1, w2 is equal to v2, and so on. All the elements in that tuple are equal for both the vectors. Now difference between the two vectors u and v. If we calculate a difference between the two vectors, then it will be just the addition and the second vector will be negative. So w plus minus 1 into v. So the answer will be w1 minus v1, w2 minus v2, and so on. A zero vector is defined as a vector having all the values in the tuple to be 0. Now a vector v can be represented as a row matrix as given here and a column matrix as given here. In the row matrix, the size of the matrix is 1 cross n, and in the column matrix the size is n cross 1. Now we will again see some more properties of vectors. Now vectors have properties such as, if we have two vectors u and v and a third vector w, then we can see that u plus v is equal to v plus u. That is commutative property of vectors. Second is u plus v plus w is u plus v plus w. This means that they have an associative property. Similarly, we have certain 8 properties which we will be discussing in the further videos. Now inner product or dot product of two vectors u and v is given by u1 times v1 plus u2 times v2 up till sum of un times vn. So this is defined as the dot product of the vectors. Now properties of inner product is that the inner product is commutative and it is associative, and if we multiply a constant to the first vector, then it will be equal to constant times the dot product of the two vectors. Also, the dot product of a vector with itself will always be greater than or equal to 0. Now coming on to norm or length. Now norm of the vector is defined as square root of squares of sum of the squares of all the elements of that tuple in the vector. So norm of u is square root of u1 square plus u2 square up till un square. Also the properties of norm are that a norm will always be greater than equal to 0. A norm will be 0 only if the vector is a 0 vector. K times norm of the vector will be equal to k times the vector, and sum of two vectors will always be less than equal to the sum of its norms. This comes from the triangle inequality. Now the next property is distance. So the distance property tells us that the distance between two vectors is similar to the Euclidean distance, that is summation of square root of summation of u1 minus v1 whole square and so on. Now angle between the two vectors is given by cos. So cos theta is the dot product of two vectors u and v divided by the norm of the vectors. Orthogonality in Rn. Now in an n-dimensional space, that is Rn, two vectors are said to be orthogonal if their dot product is 0. So u and v are orthogonal if u dot v is 0. Pythagorean theorem in Rn. So Pythagorean theorem shows that the sum of two vectors and its norm will always be equal to the sum of the squares of norm of those two vectors. Now if we try to prove it, then u plus v square will be equal to u plus v dot u plus v. This will be equal to norm of u square plus v dot u plus u dot v plus v norm of v square. And since they are orthogonal, that is u dot v and v dot u is orthogonal, we can say that this will be equal to u square plus 0 plus norm of v square. Hence proved. Now again the last thing is Cauchy-Schwarz inequality. It states that the modulus of dot product of two vectors will always be less than the multiplication of their norms, that is modulus of u dot v will always be less than or equal to the norm of u into norm of v. Thank you.